Question number 5. Sphere X falls through a fluid with the terminal velocity v. Okay, let me write down the diagram what exactly is happening. So this is the container. You would have done an IA also based on this. And then you drop an steel ball. Now this is going with a uniform velocity. Now sphere Y is made out of the same material. Okay, density is same and falls through the same fluid. The radius of the sphere Y is twice that of the sphere X, which means what? Ry is equal to 2 times Rx given to you. What is the terminal velocity of the sphere? What is Vy? That is what is being asked to you. So towards it, what you can do is, if you remember the equation, it's well and fine. If you don't remember it, you can do it like this. So you know when the particle is falling downwards over here, what forces are acting? mg is acting downwards like this over here. Then you have this viscous force, okay, which is acted upon 6 pi eta rb, and then you have a buoyant force which is given by b. So when these two forces, upward force equal to downward force, then definitely you observe that the particle will move at uniform velocity. And thus you should be writing this as mg is equal to 6 pi eta r bt plus b. What is the buoyant force? Which I can write as 6 pi eta r b plus this one is nothing but density of the liquid, volume of the object multiplied by g. This is what we write. And then this can also be written as density of the solid multiplied by the volume of the solid multiplied by g. And now I can now write rho s minus rho l multiplied by v into g is equal to 6 pi eta r into v. I'm just deriving this equation here for you so that you understand how do we get it. In fact, I can write down the equation directly, but you know, it's always good to understand why do you get that. Rho s minus rho l into 4 by 3 pi r cube into g. What is this now? This is the volume of the sphere. It should now be equal to 6 pi eta r into v. So therefore, this v is nothing but your terminal velocity. I'll write this as vt. I'll write this as vt everywhere over here. And this is your volume. This is your volume. Don't consider this v and this v. Don't cancel it. That's why I should write this as vt here. This is your capital V. Okay. And now what I do is I can now take this pi and this pi goes away, and this eta is there. This r, there is one r here. This r cube here. This becomes r squared. So I can now write this as 4. Okay, I will write it. Make it more clear. I write it as 4 into rho s minus rho l into g divided by 3, and you have a 6 here, eta here, multiply the 6 into eta, right, like this, into what I left here is this r square. So r square is equal to v. Now the whole thing I can simplify it, but I don't have time. I have very less time to do this. What I do is I write this as some constant k. So r square is equal to no square here, vt over. What happens? Vt is proportional to r square. That's what we say. So when the radius gets doubled, this is your equation number 1. When the radius gets doubled, what will happen? Vt dash becomes a k multiplied by 2r the whole square, which should now be 4 into kr squared, which is nothing but 4 times vt, right? So what's happening? The new terminal velocity will become 4 times the actual terminal velocity. And there is vo. If you are able to remember this, it's well and fine. Vt proportional to r square is a standard result whenever we say the dependence of the velocity of the object with respect to the radius of the ball, then you can use this one. If you don't remember, then this is what to know. Okay, so the answer is